enlighten us. Thank you.
Thanks very much, Wayne. I'll just share screen now. And confirming that you can see them.
Looks good.
Okay, just a starting slide here, which is really something that Australia did back in the 70s, and sorry, not 70s, the 90s, which was flown on the shuttle twice and returned to Australia on each occasion. That's a little bit of old space, but it worked. Anyway, so what we'll do is move through, and you've already given the presentation. I have to say, Wayne, thank you very much for that, but I am not a doctor. I'm just a mister. And one day I might have the time to go and get a PhD, but not just yet. I guess the origins of my perspective on this talk go back quite a long way. I've been around for too many years, some would say, in a range of areas in the international and Australian space industry, and both in the civilian and the military domains. Like Tony, we've both been back far enough to have seen how space technologies have evolved over that time. And fortunately, I've had the pleasure of having hands-on design, build, and test experience on 15 successful missions in Europe and Australia, 20 missions overall. Regrettably, Ariane dumped a couple of them into the ocean for us, but that's another story for another day. I've project managed space industry suppliers and subcontractors in Europe, USA, Canada, and Australia, so I've got a fair understanding of how to manage and what to expect from competent providers, which is very important when we depend on those competent providers. I've managed the definition phase of Optus C1D military payloads, so I've got a fair handle on some complicated issues, and I was the CEO of the former premier space company in Australia, as Wayne said, Ozspace. After Ozspace, I managed the activities of Space Systems Loral in their acquisition activities for the NBN-CO satellites, and in the early stage in the definition of those NBN-CO satellites. So again, I got a reasonable handle of things there. Then I decided to do something different and go into the optical science, and ultimately I ran the engineering program at Mount Stromlo for 5 years and put the facilities that are there, Australia's premier space test facilities, they were put in on my watch, and I'm very proud of that. And everyone in Australia should be very proud of them. After that, I decided I'd had enough of the ANU and joined CSIRO to run the International Dish Consortium for the SKA, which had me basically traveling all over the world every month for 2 years, which was very tiring. After the Australian government actually pulled the pin on that portion of the SKA work, I decided to go back into the consulting area and worked with a company called Shoal Engineering, who put me into the Australian Defence Force. And I've been working deeply in the Australian Air Force's space domain leadership area now, and that's been extraordinarily rewarding, and you should all know that our Defence Department is getting well and truly up the space pipe, which is great. So, part of my talk is about fashionable terminology. It sounds cool, but I believe it can be deceptive because it leads people to the wrong conclusions. One of those terms, of course, is old space. And you hear it, space 2.0, that's the new space. And then there's the old space. Oh, don't do it like old space. I like to think of it as a term of endearment. So what is it? It means, old space means the sorts of things that were done in the past. Great projects like surveyor, for those people who can think back to that period, things like Mariner, things like the Viking, the first landers on Mars. Voyager, everybody knows Voyager. That was all done using old space. Apollo is what we consider to be old space. Even the Saturn V is what is referred to as old space today. But those were great projects. They did extraordinary things, some of which it took us a lot longer to do with new space methods. What else does it? Well, it also includes these sorts of things. So instead of those interplanetary missions, now we're talking about more mundane commercial missions that Tony and I worked on, for example, MARIX and ECS. These are commercial communication satellites. In the early days, these were groundbreaking new technologies. Olympus was the largest satellite of its time in the day. And that's pretty interesting. That's actually in the JPL, large thermal vacuum chamber, and that rather handsome young looking guy right there was me when I was young and handsome, if I was ever young and handsome. That old space also included Australia moving for the development of a light launch vehicle that would have supported the onesie-twosie launches of the original Iridium constellation. Australia had a US presidential license to import a Peacekeeper class commercial first stage. So this is not little sounding rockets. This is big stuff, putting tons into orbit, not little things. It also is, old space is also the technologies that launched such things as NVSat, which aboard which we actually had Australian-made hardware, made here in Canberra, Australia, by the company I used to run. So I'm very proud of that as well. And that old space includes things like FedSat. If all of you remember FedSat, it was a successful mission. It was a difficult mission, but it was a very successful mission. And we should also be all proud as a nation of that. So that's old space. That's what's considered as old space. Surprisingly, so is the shuttle. The shuttle is what you would consider as old space today. Also these. Today, the current large missions that we are using from a military perspective, like WGS, we're using commercial communication satellites, Intelsat series, for example. This is just as an example. The high resolution optical imagery satellites that service our commercial markets, that might be considered as old space as well. 0.31 meter ground sampling distance commercial imaging satellites, that's considered as old space, but it's pretty cool stuff. Our NBN Co satellites could be considered as old space. Why is that? And it would also appear that one of the founders of the small sat revolution, Surrey Satellite Technologies, 40 years of small satellite expertise, and yet they could be considered as old space as well. So old space means the way that things were done back in the day. It was really an achievement of space activity using technology that was at the state of the art at the time. And more importantly, that was appropriate for the mission requirements. And we'll talk a bit more about this as we go on. Was it bad? Hell no. It worked. It worked very well. So did it work? Hell yeah. We shouldn't be dismissing that level of technology as saying it's old space. It's not. Is the approach still appropriate? Yes, absolutely. Most commercial And mission critical satellites are still built to high performance and high reliability standards using, again, the most appropriate technology of the day. Very important to keep that in mind. Why? Because commercial missions need to deliver high performance. Importantly, commercial missions can't afford to gamble on the uncertainty of a revenue stream after having spent a great deal of money putting that into orbit to achieve high performance. Not all missions need to be high performance, but when you're delivering and guaranteeing to deliver high performance, you better be sure that your investment is going to work for the time that you expect it to. And that's a guarantee of reliability that you can't always get with some of the new concepts. So can you afford to gamble? No. And who could afford to gamble? Well, actually nobody, because unless you've got unlimited funds, you can't gamble. Even very rich folks like the current president of the United States can't gamble. So new space, a great term, new space, the revolution that's coming. Everything's going to change with new space. What does that mean? Well, new space implies faster, cheaper, smaller, more agile, better in every way, and using every new generation superlative that you can think of. Or is it? It implies Cubesats, miniaturized electronics, highly integrated subsystems, standardized form factors, and a plug and play concept. That's actually great. And, you know, new space is achieving that, provided it's done properly. Very important. What does properly mean? Well, it implies also a theoretical global space parts supermarket from which you can buy your parts, bolt them together, and bolt them into a functioning satellite. Does it? One hopes so. That's the promise of new space. It implies lower launch costs and an overall lower cost of access to space. But it's not free. And that's true. It is providing a lower cost and an overall lower cost of access because you're launching much lower masses into space for missions that are appropriate for new space technologies. Does it mean more reliability? Actually, no, it doesn't. And it hasn't demonstrated to be that. It could, but it hasn't yet. Does it mean more performance? Well, no, there are physical barriers to the performance that can be achieved from a new space Cubesat concept, even a larger microsat. And we are dealing with just physics. We haven't learned how to bend physics yet. When we do, things might change, but for now, we're still limited by physics and the engineering that goes into making these systems. Does it mean more resilience? This is a subject that's often flaunted as a great savior, or that Cubesats are the great savior of. And yes, for an appropriate mission where you can deal with the performance limitations of a Cubesat and you can launch a constellation, you get resilience from the constellation. If every one of those Cubesats was highly reliable, you would have greater resilience, perhaps more cost, but higher resilience as well. So routinely, based on some of the plug and play concepts, it does not necessarily mean more resilience, but it can do, even if you've got a whole constellation of unreliable satellites. Some of them will work. And if just one is enough to service your mission requirements, then okay, you are achieving resilience, but it doesn't always mean so. It also means these. So when we're talking about Cubesats, the concept of a CubeSat is a standardized form factor, this 100mm cube, 1U form factor, 1 unit. 3 U's are becoming much more prevalent than perhaps 1 U's. And because they're slightly larger, you can do slightly more with them, which is a great thing. Then you're starting to move into larger multiples of this standardized form factor, a 6U format that you can orbit quite a lot of capability in. And that's now starting to get interesting in terms of performance potential. Then you go even further into things like the 12U, and there are larger still form factors that can be established. Now you're really moving out of the CubeSat, nanosat concept and into more of the microsat and even larger small sat concepts. So now you're actually getting into an area where performance can be achieved because your physical boundaries, the limitations of your physics, are also expanding and giving you more opportunity. It also means missions like Australia is working on today, and this is a couple of CubeSat missions that are part of a program that the Australian Air Force is supporting for research purposes. It even means that we can launch small satellites, CubeSats maybe, but certainly microsats and larger form factors of CubeSats into cislunar orbits. And that's something that is actually in planning and underway, not necessarily in this country yet, but certainly in other parts of the world where we have established space communities. Will new space replace old space? Well, there's a lot of people who say, yes, it will. But I'd say, no, it won't, because new space colloquially represents the adaptation of the space technology of the day. So today's new space is tomorrow's old space. But it's really just a continuum. In a number of cases, it will provide more rapid access to space and can perform some functions well, some very well, many more poorly than the old space concepts of high performance, high reliability missions. It provides the research community unquestionably with a cheaper access to space. But again, it's not free. And we don't want to gamble because it's not free. The concept of nano and micro satellites definitely have capability. They will not, however, replace the bespoke performance of critical commercial and military missions. They will no doubt supplement them and work in an aggregate unison, but it's highly unlikely that they will replace some of the more specific assets that orbit the Earth, especially in high orbit, because, again, of physics limitations. And physics comes into play when we speak about things like optical performance, communications link budgets, and power generation, and of course, mission lifetimes. All of these things are physical limitations that do constrain the concept of new space, the CubeSat area, to mission limitations. They are constrained. To date, unfortunately, with a few exceptions, the Cubesat community has really had a pretty bad mission reliability record. And when you look at the statistics, you're depending on who you believe and how success is reported, that success could be, yes, it turned on when we got to orbit. But did it work thereafter? Did it actually achieve your mission objectives? Well, depending on how you interpret success and failure, you're looking at in the order of 20 to 50% failure rates in the CubeSat community. That shouldn't happen. For one thing, you're putting up junk into orbit, and as we'll talk later, there's way too much of that already there. So a little bit of fun facts about history. When the space industry really started 40, 50 years ago, we were actually building small satellites. That was the norm. That was de rigueur, because we didn't have the means to build anything bigger yet. The sort of technologies, the state-of-the-art du jour that we had at that time was based on the way we understood how to build aircraft. So when you looked at some of the early missions, they looked very much like aircraft frames, riveted panels and tubular struts and such like, because that was the process we knew at the time. Early components and materials, we didn't have as much knowledge as we do today about the performance of componentry, electronic componentry. They were still discrete electronic components in those days. And as a result, everything was over-designed to compensate for that unknown factor. When Tony and I were working in the space industry in Europe, TRW still existed. It's now Northrop Grumman today, but the TRW used to pride themselves in building a satellite with a guaranteed 10-year life with a 99.999% reliability factor for that 10-year life, and then celebrate the fact that it actually lived for 15 or 20 years. And of course, everybody said, well, hang on, did I just pay for over-design? And yes, they did. But that was the state of the art of knowledge in the day. Electronics components were individually tested, in leading to this term space rated in those days because of manufacturing variability. Today, the manufacturing process have become much more consistent, more repeatable. So it's allowed the use of almost COTS componentry in some of the Cubesats and small satellites. But again, that's life limiting, and we don't know for sure how long some of those things will live. But we are learning from the Cubesat deployments how long some of those components will actually survive in the vacuum and radiation environments of space. In the 70s and 80s, we were still learning a huge amount about the space environment. When Tony and I were there, we were learning about electrostatic discharge and how to deal with it, how to protect a large satellite that's constantly being bombarded with high energy electrons and stopping it from creating stratified charges, which would create electrostatic discharges and creating, in effect, small EMPs and disrupting spacecraft function. SSTL, Space Systems, Surrey Satellite Technologies Limited, was perhaps the first vocal proponent of commercial micro and small satellites technologies. Sir Martin Sweeting led that charge through Surrey University and has done fantastic work over that time. SSTL promoted faster, cheaper, smaller. We heard that terminology before? Yep, it's coming again, and we hear it again, so we should be familiar with that today. The inventors of the CubeSat concept did it so that they could make space easier for researchers to access. I keep forgetting the other guy, but Professor Jordi Puig-Suari, who's somebody I consider as a friend, was one of those founders. And interestingly, it was their hope at the time that by having these standardized form factors and standardized processes and methods, that there would be an international space parts supermarket that could be created and from which people could just buy the parts and put it together. Didn't quite turn out that way, but it's close. The consequence of it didn't quite turn out that way was that the the Cubesat inventors started a company called Tyvak. I'm actually loosely associated with Tyvak, and they're a very good company, very capable company. However, even Tyvak discovered that the space supermarket just was too unreliable, too inconsistent. The quality of the products was too variable. So today, Tyvak is an industry leader in the Cubesat to microsat class of mission, but it does pretty much everything vertically because it's the only way they could control the quality of all of the parts that make up their satellites. If you didn't do that, you're basically playing roulette. So let's do a quick reality check. Despite our infatuation with Cubesats, they cannot do everything, and they will not replace high reliability platforms providing critical services. That's at least today, and within those physical limitations that I speak about. So it means that we may be able to make them more reliable, but we still won't be able to get past the diffraction limited performance of a telescope when you are comparing a 100mm diameter optic as compared to a 1-meter optic, both operating in low Earth orbit, nor the power generation that's required to drive the large multi-tiled focal plane arrays behind the 1-meter telescope versus the small focal plane array being driven by a Cubesat. So, you know, those physical limitations still are not going to change yet. Maybe in the future, maybe things will move, and that's part of this evolutionary process. The rigors of space cannot be ignored. Ignore them at your own peril. It is still a harsh environment out there, and whilst we have components now that are more repeatable, more well understood, it doesn't mean that you can just bolt a whole bunch of bits together and throw them into orbit and expect them to work. Space will get you. Don't ignore the rigors. To not ignore the rigors means that you need to design, verify, and validate your Cubesat processes and your spacecraft just like you would any old, in inverted commas, spacecraft. Because if you want to be sure that it's going to work, there is a process that you need to go through to ensure that the rigors of space and that your design will survive both the launch ascent and operation in orbit. Taking shortcuts with Cubesats, or for that matter, any spacecraft, is just playing roulette. If you're cutting corners, you better know why those corners are there. If you don't understand that, you're just playing roulette. And that means you could lose. So how much can you afford to lose when you play roulette? Can you afford to spend a couple of $100,000 or a few $100,000 repeatedly building and launching a Cubesat only to find that it fails each time you put it in orbit? I sure as hell can't. To try and stop the failure rates, we should be looking at what are in existence today as proven international standards and processes for your design activities. Australia's been sitting on the bench for about 40 years or more. We've had a few flutters along the way, and I've certainly participated in those flutters happily, but we haven't consistently tried to establish a sovereign capability in this field. The result is that pretty much every other spacefaring nation in the world is way ahead of us and is better at doing stuff in this field than we are. We should be learning from their mistakes, and we do that by utilizing those international standards and applying them and learning how to apply them. Reading a standard is one thing, implementing it is another. And for those of you listening, I highly recommend using the processes that are free and tabulated in full form in the European Space Agency's ECSS standards, the European Collaborative Space Standard, which is an implementation of system engineering, quality, software, all of the standards that you need to build stuff, build complex multidiscipline systems. And because the European Space Agency had different nationalities, different languages, different companies, different countries, all participating in their programs, they found that you could have 10 people around the table, all saying they complied with a particular standard, and every one of those had done a slightly different implementation of that standard. And when everybody said blue, every one of those 10 people would have a slightly different interpretation of what blue was. So ESA said, right, we're writing the implementation, you will use this implementation. Therefore, when everybody says blue or red or green, everybody will know exactly what blue, red or green is, no matter what language you spoke, no matter which country you came from. And for that reason, it is a great set of documents, templates that embody all of those standards. And we should be using that because it means that we will then be compliant with the international environment. And NASA also recognizes the ECSS standard. And NASA itself has a great systems engineering handbook, but you have to perform your own implementation. So take heed from that. Learn from other people's mistakes. Always assess your mission requirements and then find a solution that meets those requirements, not the other way around. You might even find that you don't need to use a space mission to achieve your outcomes. Too often, I'm an engineer, I'm guilty of this as much as anyone, that you want to build something to go into space. And you may find a reason to do that rather than the space mission being the solution to a need. So let's be intelligent about all of these things and be at least clear about what the mission requirements are, even if it's just research. Fine, be clear about what it is and then build the solution to suit the mission requirements, not the other way around. Now, importantly, always play to win and design every mission for success. Now that may seem pedantic and boring and all the rest of it, but you know, to build stuff that's going to work exactly as you designed it to work in orbit for exactly the length of time that you hoped it would work for means you got to do some boring process stuff to verify and validate that that's what's going to happen. So don't shy away from that. That's why those fabulous test facilities are up at Mount Stromlo and are being replicated to lesser degrees in various places around the country. So do that, use it. Success breeds success, so be successful. If you hope to, even in the research community, get further research funding, and repeated research funding, how often are you going to get that if you keep failing? If you succeed each time, then you're more likely to get that funding if you're succeeding. And that's true in the commercial environment as well. If you try to build something for the commercial space community, such as it is, and every time somebody buys something from you, it doesn't work, you ain't going to be in business for very long at all. So be successful, plan for success. Plan every mission to be successful. And you can't cheat physics. And good engineering always aids innovation. So be aware of what you can realistically achieve. There is no magic. We haven't bent physics yet. Make sure that you understand what you realistically can achieve. So some recommendations from Franzen, if you haven't heard enough already. Analyze your mission problem requirements. properly first. Do a proper requirements analysis. And that's actually one of the documented processes within the ECSS template set. If a Cubesat fills the bill, then great. If it doesn't, don't force it to fit, because you're more likely to fail. You're in effect forcing it to fail. Now, I work in an area in defense at the moment which deals with space domain awareness. That is, the clutter that's up there and understanding what there is. And everybody wants to deploy a damn constellation. Well, go and ask Mr. Donald Kessler about that first, and then return to item 1, which is analyze your mission problem requirements properly first. If it still is best done with a constellation, then design it properly so that you minimize that. The LEO orbit especially is becoming highly contested, highly congested, and it's getting worse. Today we can track better than 20,000 objects in low Earth orbit and in the medium to high orbits. That will more than double over the next 10 years. And Mr. Musk is making sure that's going to happen and is well on the way to achieving it. Interestingly, SpaceX and the Starlink satellites are not Cubesats. They're 200 kilo old school style satellites because there are limitations to what you can do. So Starlink satellites are about 200 kilos apiece, not Cubesats. Engineering, and especially space engineering, is a team sport. And my recommendation to you is that a champion team will always beat a team of champions. So what? Well, a winning team needs the best players, so select your team carefully. It needs the best captain. Make sure you have somebody who's leading that team well. And it needs the best coach to coach the team. And also the best game processes. With all of those, you're going to win, but there is no room for prima donnas. Organize your team properly. Always, always play to win. Don't waste your money. Now, to finish, I hope this video will work, but it's a demonstration of a process that the company I used to run went through in the remanufacture of a $5 million optical instrument for the Mount Stromlo Observatory after the 2003 bushfires destroyed the observatory and the original form of the instrument. The instrument, when we sought to remanufacture it, had a lot of undocumented features, shall we say, from the remains of the instrument that we had. And it, let's just say it was interesting. In rebuilding it, we did this in a class 1000 clean room. It was using the precision integration and test methodologies that the company had built space hardware using. And, excuse me, I've gone back. Thank you. This is what it looked like. A little bit faster, and for all of you who remember Benny Hill, I apologize for stealing his music. This is the level of precision that you need to actually work at. Not for everything, not always for Cubesats, but that work led to an interesting revelation. When the instrument was delivered to the Gemini North Telescope on Mauna Kea in Hawaii, my team were asked, how do we disassemble it? And my team asked, why do you want to disassemble it? Oh, so we can figure out how it works. And unbeknownst to the Mauna Kea team, there was a complete end item data pack describing all of the functions, all of the dimensions, the drawings, the performance, everything that was delivered. They'd never had that before. And which was the underlying reason for them asking, how do we pull it apart? Because they would usually do so and then figure out how it worked and take steps. The consequence of that precision integration meant that that instrument worked first time. It is still the only instrument that Gemini North has ever had that worked first time, and it is still referred to as their gold standard. So there is method in the madness, shall we say, for doing things properly, thoroughly, and rigorously. Now, you've seen this slide pop up a couple of times, and it's the truth that I'd like you to remember, that there is no old space, there is no new space, there is just evolving space as the technologies and materials of the day permit. Tomorrow, the technology today will be old space. There is no magical wave of new physics that is letting us do things differently. We are simply applying the technologies of the day to do things slightly more efficiently, slightly better, slightly more compressed, with slightly less power requirement. But there are still physical limitations that we can't ignore in what we do. And as long as we keep that into perspective and realize that Cubesats are not going to do everything for us, and if we want a sovereign capability, we need to be looking to build more performant and more reliable, larger missions as well as Cubesats, then we will have a chance of moving forward. But to do that, we need to have the discipline in all of the processes, in engineering companies and at universities, to perform at that level of rigor. Ignore the rigors of space, and I guarantee you it will bite you in the ass. And there is no way around it. The rigors of space are tougher than we are, so we need to take steps to live with it. That's the end of my presentation, and I'm now very happy to take questions. I will relinquish the screen to you, Wayne.
Excellent, Roger. Thanks very much. We've got some questions. This is the first one coming up. Do you want to look at the chat, or do you want me to read them out? I'll actually
probably best if you read them out, if you don't mind.
Just go down. John Lee had the first one. Okay. John Lee says, "Hi, Roger. Have the Russian and Chinese satellite implementers suffered a deterioration in standards similar to that you described for the recent Cubesats?" Oh, okay.
Well, interestingly, China, and I do apologize for the phone ringing in the background, but it'll pass in a moment. The Chinese are actually remarkably good at what they do. The Western world has given China all of its aggregate technology in the way that we have subsequently asked them to manufacture everything for us. It's not their fault, we've given it to them. And being smart people, they've figured out how to extrapolate that technology and build things. Russians, it's interesting looking at a Russian mission and a Western mission, for example. The Chinese are very much more Western oriented. Some of their early stuff was based on the Russian technology, but they've moved more towards the Western style of technology. Russians used to, for example, if you had to put something in the vacuum of space, instead of making everything space vacuum tolerant, they created a pressure vessel and would actually put the main payloads inside a pressure vessel. But of course, there's no convection of air inside there, inside that pressure vessel in orbit. So how would you naturally cool it, etc.? Well, you'd put a fan inside. That's exactly what they did. Now that's some of the early technology. I'm sure today it's evolved much more towards modern Western style technologies, and because componentry is more available. During the time of the USSR, when that technology wasn't available, that's the way things moved. And there was a lag, obviously, after the wall came down and the industry in Russia started building things differently and started assimilating more Western technologies. I hope that answers the question.
Sounds like it could.
Yeah, thanks.
Excellent, thanks, John. I've got next question from Julian Grodzicki. Well, this is an interesting one. Bit of a suggestion here, I think, indirectly. Is there a space systems engineering book of knowledge in the offing besides the NASA handbook?
Yes. Actually, there's a number of books that are very good that assimilate all of the system engineering technologies. And SMAD, Systems Engineering Management and Design handbook is a great one. If you want to have a single source of a lot of information. Again, I'd recommend looking at the templates that are provided in ECSS, because they're in effect documents which describe what you need to do. But yes, there are systems engineering handbooks. They're not emergent, they are in existence, and therefore you only need to look online for them, and I'm sure you'll be able to get them.
Okay, that's good. Next question from Alan Hasselton. There seems to be a divergence of opinion about the congestion in LEO. Is it or isn't it an issue, or is it not now or it soon will be? I suppose that's just how bad is it getting and when's it going to become a problem?
Without breaching my own conversation limitations, I can assure you that it's getting worse. And it is becoming much harder to keep track of everything that is there. At some point, and here's an opportunity for a commercial opportunity for somebody in Australia, every satellite, whether it's a CubeSat or a large craft, should have a self-dependent transponder on it that can operate even when the satellite itself has died, just reporting its position, because tracking all of that debris in orbit, all of those other dead satellites and such like, especially low Earth orbit, is getting harder and harder and harder. It used to be that the US had sufficient capacity on its own to do that. It no longer does. It depends on everybody contributing to the knowledge base. As things get worse, it will become much more important, and it will probably become a subject of ITU registration, resident space object registrations, that those sorts of persistent transponders will be a requirement to the point when missions are re-entered. And that function will probably become a mandatory requirement as well. At end of life, you will have to be able to deorbit your mission. When you're out of GEO, that's not possible. So you have to push it out a bit further. In MEO, it's harder, but still possible. So yes, it is a real situation, and it is getting worse.
Yeah. No.
What I can say is that the current warfighting domains of land, sea, air, and cyber, that's 4. The 5th warfighting domain is space. So it is very serious.
And Alan just added to the end of it, says, or a deorbit system, which is probably another alternative to the problem we've got with junk.
Yes, yes, absolutely. While it's still orbiting, you need to know where it is, and then you should be deorbiting it.
Yeah, good one. Okay, thanks. Janine Gertzen has a question. If the satellites are used for global environmental monitoring to gauge comparable efficacy in our land and our fellow signatories' performance. Okay, sounds a bit like a you. Is it possible to gain better cost benefits from number rather than size? Okay, so yeah, right, constellations. How is new space built for purpose being economically evaluated?
So is that asking, is it better to have a constellation than single? Yeah. If you have a temporal coverage requirement, that means you need to frequently update information about an Earth observation matter, such as climate dependency and such like. Yes, having more eyes looking at the ground is better. But if every one of those eyes is looking at an area of ground that may be 50 or 100 kilometers in width because you can't put a higher resolution in your mission, is that going to be better than a high resolution mission? Maybe, if that's what your mission requirements accept. If you can tolerate those mission requirements, then yes, do that. And yes, you'll have resilience and you'll have probably lower cost to orbit. You'll also have more junk in orbit. The reality is that in the past, we might not be able to achieve persistence over an object from geo orbit. Today, commercial technologies are allowing us to achieve quite reasonably high resolution persistent observation from geo orbit. So there is every argument today, for example, to host a fire monitoring payload on, say, the next Optus mission, for argument's sake. And that would be better because it's more timely, it's looking all the time, than having 10 or 20 small satellites orbiting the globe, just looking at us as they go over. If what you're trying to do is sell that capability to others, okay, do your mission design to understand what your requirements are. And this is what I'm getting at. Sometimes it is appropriate to use a small satellite, sometimes it's not. And you need to do that mission design properly to understand what your requirements really are. I hope that answers the question.
Okay, thanks. Another question from Crystal Forrester. As you have said, Cubesats are currently not very reliable. What do you think would be key things to correct or address to increase the reliability?
Hi, Crystal. Great to hear from you. Really, it's the process. I've been working with UNSW for the last year and a half as Defence's representative to oversight what they are doing. Perhaps more as a coach, going back to that team analogy. And the installation of processes to ensure that test, verify, validate by test, so that when you actually build something, you are certain that to the extent of your budget and design, you know it's going to do what it's going to do. Do not cut corners unless you actually know what they're there for. So it is boringly process dependent, and follow those processes. Go back to ECSS. All of those processes are spelt in there. In fact, if you took the whole set of documentation, which is from the requirements analysis down to as low as high rel soldering, that's enough to take you to Mars, or tailor it back to what you need for low Earth orbit CubeSat, and it will get you there as well, and reliably. So don't ignore these processes. They're there. They've been written by really experienced people that have done this and are doing it repeatedly. So if you want to make your CubeSat more reliable, follow those processes.
Okay. Yes, thanks. Crystal says thanks. Okay, have we got any other particular questions for Roger? One thing I'd definitely like to do is to thank Roger very much for his time. It's a very interesting talk, looking at basically the change in definitions of space and how it's worked out. So I thank you very much for doing that and answering the questions to us. And it's been a tricky year in total trying to do do some things, but at least I think things are starting to come a little bit back more to normal. And at least maybe next year we can have some things to look forward to instead of all being stuck in the house. I think it's probably the worst I'd use. So
fingers crossed.
Yes, fingers crossed. Anyway, I'll certainly be hanging on for a little while, but I'd like everyone to thanks very much to you, Roger, and for your time tonight. And we can all put our hands together to you tonight. Worst I can do for that. Yeah, thanks very much. And I will be on for a little while after Roger completes the talk anyway, if you want to talk to me about various things, and we'll get into, yeah, somebody's got the hand emoji up there. I should have said, go and use those. Oh, okay. Somebody's asked.
Hi, Eva. How are you doing? I see you hiding there.
Oh, I'm in prime view.
Lou's got one question for you at the end there. Would you like mention about Elon Musk satellites? Probably about Starlink, I think. Anything to say about that in particular?
Yes, Elon actually has built in the ability to, one, report where his satellites' positions are, and also to deorbit them at the end of their mission life. But again, you know, he's somebody who decided that the industry was too variable, and he's just done everything vertically. SpaceX is a highly vertical organization. Incidentally, the CEO of Tyvak is somebody who worked at SpaceX and helped it get to where it was. Has just decided to do something different. So it's important to realize that every satellite manufacturer, whether you're a lab at a university or a commercial one, has a responsibility to consider what the space environment is becoming and how to mitigate that. Just be aware of it. Elon is. Even if he's putting too many up there. Say again, Eva?
I was going to say, I suspect Elon's more motivated by the money, actually. But if you don't mind, I was going...
Elon's a funny character.
But it's not just the money. I mean, he's also interested in actually creating a capability, and he's been very impressive there. I was going to ask a question, but I couldn't type fast enough. Just about the amount of time that it takes and money that it takes to follow the processes that you're mentioning. Because at least my intuition is that it's probably, oh, I don't know, factor of 3 in time and probably 5 in money.
No, actually it's not. I would challenge that, and I would counter with how many. If you build your satellite for 100,000 and launch it, I bet you couldn't do it for less than that. How many times can you afford to fail? Yeah, how many times can you afford to re-spend 100,000 or 200,000?
Yeah, the question's where the cost-benefit analysis is, and I'm not sure, because I do know that cost of an engineer for a year is of order 150K. So if you have 2 or so of those, which I can't afford it, and you have them working for 2 or 3 years on defining your requirements and so on.
Oh, it doesn't take that long. It doesn't take 2 or 3 years to define requirements.
No,
it just takes,
it's the iteration, it's the test. I mean, testing's really important. That's one thing we've actually done increasingly more on. But it's at the moment, there's a real issue in Australia anyway, and this is probably true more worldwide, in terms of the amount of money that's available for many of us to try and do things in space. And, you know, if you've got to, if the consensus is that one has to spend, let's say, oh, I don't know, 6 person years engineering to do a viable satellite, and you have to spend, well, and then you've got to add on the costs and so on, and you've got to design an engineering model, and you've got and build one and test it, and you've got to do a flight model.
You will have a flat sat. You need to have some means of verifying your electronic, not just your mechanical, but your electronic systems, hardware in loop.
The flat sat's the way that we've tended to do things,
Yep.
and
It's a good solution.
and so on, and it's a great way to go. But it's, yeah, I mean, it's a matter of money. I mean, I talk, you know, reasonably often to Russell Boyce. I had a project I wanted to do, which, you know, my sort of budgeting would have been $500,000, and Russell said, "Oh no, I couldn't do that for anything less than 2, if not 3." And, you know, it's partly a function of the amount of money that he has available via the Air Force and DST and so on. Most of it non-competitively won, by the way. But it is one of those things, you know, the amount of money makes a big difference. And you know, so if you have to, if you're so worried about failure that you spend 6 times the amount of money, but your success rate was 50%, then in one sense you've spent 3 times the amount of money than you needed to do the one. So so I'm not sure where, I think one of the things we all have to work out is where that balance is. And I don't know where it is. I know what I can do.
I quite agree. And if we go back to the concept of the standardized form factors, the standardized components and such like, if that was truly achieved, that would make your job a lot easier. The problem that I've seen, and Russell will tell you this because he's fallen foul of this as well, is that the actual space supermarket is selling some pretty crap stuff.
Mm-hmm. Oh, yes, sometimes that's exactly right. And it's not commercial off the shelf either. It's more like commercial to order and wait for a long time. It's just not commercial off the shelf, and it's not plug and play at the moment. And that's, of course, one of the things that some of us are trying to change. But at the moment, yeah, it's not a simple supermarket. And
No.
Things don't always work the way you expect them to.
No, and the plug and play part hasn't worked either for the simple reason that there are so many different formats, which is why Elon is doing things vertically, which is why the company founded by the inventors of the Cubesat concept is vertical now as well. It couldn't do what it's doing. It couldn't be as successful as it is by relying on the space supermarket. And that sadly is the reality of the industry at large today. Now, if you are building your own equipment, and Innovor, for example, in Adelaide is doing that. They've found the same thing. They're building their own kit. If you have a standard of service subsystems for your Cubesats that you can step and repeat, that you prove, you go through, you step and repeat, then you have the confidence that they are functional, and that as part of your system bubble, they are plug and play, then your costs for your missions will come down. But if you have to rely on buying stuff from the supermarket, it's sadly not going to be cheap. Ask Russell, and part of the cost of what he's doing is because he's actually having to resort to building a lot of stuff himself as well, or his team.
Yes.
And that adds the cost, but it also adds to the reliability of the mission. We all know that M1 was DOA or did not respond. And to be honest and to be fair, there is no way of us knowing what failed other than, here's an interesting aspect, the procurement of the launch was through a launch broker, which purchased a dispenser upper stage from SpaceX. That dispenser upper stage carried 60 Cubesats. It was not 3-axis stabilized. The consequence was that when it separated from the main booster phase and started dispensing the Cubesats that were on board, it was tumbling. And 20 out of the 60 Cubesats that were launched from it were DOAs. Did they bump into each other? Were they all failures? It's not clear, and we'll never know.
Yeah.
So there you go back to the procurement process, which is why I mentioned this step of understanding who your suppliers are, what their capabilities are, and what they can do for you and reliably, and doing that assessment of who you're going to buy from and what you're going to get. So that's an important step that Russell learned. Don't use that broker anymore.
Well, or make sure that it's a 3-axis stabilized dispenser.
Yes,
Mm-hmm.
that's right. And M2 Pathfinder, which was the follow-on, had a lot more rigor built into it as well. And after the failure analysis, a lot of lessons were learnt, and those lessons went into M2 Pathfinder. So that's a boring process, but it meant that they didn't make the same mistake twice.
Mm-hmm. Mm-hmm.
And that's good. Try not to do that twice.
Yeah, it is good. You don't want to do that, but it's also a matter of budget, you know.
Yes.